So, hello everyone. Thank you for joining the Corundum developer meeting today. So I'm going to go ahead and go through these status update slides here real quick. There's not a whole lot to say. Let's see, we've got this FIFO memory inference bug that we're going to, check up on. Then the priority flow control, the AXI virtual FIFO. I've been making some modifications to the simulation models to support simulating DRAM and HBM in Corundum, basically. And then I also have some updates on the switch version of Corundum. All right, so first up, the FIFO memory inference issue. I mentioned this, every meeting pretty much. Not sure, so I'm not going to go over this in detail. Ulrich, do we have any updates on this? I think the latest from Intel is that you guys should test it with the latest version of Quartus.
Yeah, that's still the same status. We really need to go and circle back to this.
Right. Well, I'm starting to do a little bit of work with the Intel devices on my end as well for the, associated with the research at UCSD. So if you guys don't get around to it, I might be testing this myself and see what happens. So we'll see. I have the latest version of Quartus installed. I think I've built a couple of different images. I haven't tested anything on the hardware yet. So I think it's more of we'll drop it on there and run iPerf and whatnot. And if we're seeing those kernel messages, then we know it's still a problem. All right, so not much to say about that. Okay, so moving on to priority flow control. I'm starting to chip away at some of the components required for PFC to work. The main thing, so we have somebody who's taken a look at the kind of PFC pause frame handling, the generation on the TX side, the reception on the RX side, and managing the quanta counters and whatnot. But that's only one piece of the puzzle. That logic then needs to be connected to the queuing infrastructure and whatnot inside of Corundum. So I'm taking a look at, what these queues are going to have to look like to support not only potentially multiple ports, but also multiple traffic classes on each port. And, how to put that all together in a way that's going to be relatively efficient. And then there's also some outstanding questions in terms of how to integrate all this with the host network stack and whatnot. So we'll have to, we'll cross that bridge when we get there, basically, once we get a lot of the internal hooks in place. So what I've been looking at is the per TC per port queues. And the idea is to have sort of a shared memory setup where the data that's, going out the door will be organized into basically queues on a per TC and per port basis. I put together a relatively simple implementation that basically divided up the memory into fixed size blocks. But the problem is, that only works efficiently if you have like the power of 2 ports and the power of 2 TCs. And if you're not using some of the TCs, then it wastes some of the memory. So when looking at the some of the ideas for building the switch, we found the IBM Prisma switch architecture paper that has an interesting idea of using FIFOs to manage the memory addresses. So you have one FIFO that stores the free addresses as data comes in. You will pull addresses from the free address FIFO and you'll write to those locations. And then you'll take those addresses and you'll put them in separate FIFOs on a per port, per TC basis, whatever, which you'll then do the arbitration on, and then you'll read from those addresses after the arbitration. So this works, but I'm not sure necessarily how scalable it is, because if you have, say, 4 ports and 4 traffic classes, then you need, basically n squared queues, right? You'd need 16 queues in that case, and they all have to be the same depth as the backing memory. So one thing I'm wondering about now is, okay, how much block RAM is that going to consume and whatnot? So what I've been thinking about is, okay, is it possible to, instead of using a bunch of FIFOs, to do something with, say, linked lists? Because since the shared memory has basically fixed a number of blocks, well, if you link those all together with a linked list, you just need one, next pointer per entry. So it doesn't require very much memory, and then you can turn that into as many linked lists as you want. So the idea is you should be able to accomplish kind of the same thing of dividing this this memory up into per TC per port queues, but you can do it in a way that doesn't require using a whole bunch of additional block RAM. The problem, though, well, there's kind of two problems that I'm wrestling with right now. One of them is that we need to operate not in terms of these individual blocks of data in the memory, but we need to operate in terms of packets. So a packet comes in. Once the entire packet is sitting in the internal memory, then we can trigger the transmit operation on the other side, because you don't want to have a case where you have, say, 4 ports feeding in at 25 gigabits per second with the internal connection being 100 gigabits per second. And if you start sending one of these packets before it's completely written into the internal memory, well, then you're going to be limited to reading stuff out at 25 gigabits per second. So we need to buffer the entire packet before forwarding. And as a question of, is there an efficient way to do that with linked lists such that everything works? Maybe. But the other issue, potentially a deeper issue, is I'm not sure how efficient it is to actually walk a linked list on an FPGA. The problem is that when you read the next pointer, you have to turn that back around as quickly as possible from the data output back to the address input. And if you have any kind of pipeline delays associated with that, then that's going to drastically reduce the throughput, right? If you have one additional pipeline delay, then that's going to reduce the throughput by 50%. So I'm not sure if anybody's aware of any ways of kind of accelerating linked list traversal, but I'm thinking I almost need to look into doing some sort of a hybrid approach where instead of having maybe one next pointer, you can read out, it's like some combination of a linked list with arrays. So like each entry, instead of containing one next pointer, contains like 2 or 4 or something like that, such that you can actually make some progress reading some of the data and fill up a pipeline while you can turn the next pointer around and start reading the next entry. So this is kind of what I'm working on at this point. Just haven't written any code yet, but trying to figure out kind of the high level of how these pieces are going to fit together and how it's going to work. But once that's done, then this will be integrated into Corundum to replace the TX and RX synchronous FIFOs, such that we can support multiple traffic classes. All right, and then the AXI virtual FIFO that I've been working on for quite a while. This is nearing completion at this point. It's working in hardware at 100 gigs line rate. The reset and control connections are mostly done, along with all of the clock domain crossing and whatnot. I'm in the process of updating the Corundum designs to support the RAM simulation, and as part of that, well, that is mainly to support the DMA benchmark design updates that will enable testing of the DRAM and HBM interfaces using the kind of core virtual FIFO components. So basically, once I get this stuff squared away, then I'm going to get all the components pushed up to the repositories. So as part of this, like I said, I'm updating the simulation models to better handle the DRAM and HBM. So there's a couple things that I did. The first one is I added this module called sparse memory to the CocoaTBX AXI components. And basically the idea with this is that it supports arbitrarily large address spaces with a sparse cache. So previously, when you created any kind of a RAM in CocoaTBX AXI, what it would do is create a memory mapping. And the problem with that is you're limited in size to whatever the system memory supports, right? If you have 32 gigs of RAM in your host system and you try to create a 128 gigabyte memory map or something, it doesn't work. But with the sparse memory, it's just using a Python dictionary of blocks, a fixed size blocks, and it only puts something in this cache when you write to the memory. So you can create, you know, a block of address space as large as you like. And as long as you don't write more data to it than you have system memory, then it works fine. So for a lot of, you know, testing stuff and verification, you know, this is going to work pretty well. And then I'm also looking at adding the DRAM and HBM interface components to the Corundum simulation models. So this is mostly done at this point. I need to get a few things cleaned up, and then I'll push that up to the repository. So the idea here is it creates all of the DRAM and HBM channels based on all of the configured parameters. And it also supports things like the HBM internal switch, where, you know, if you have, you know, on Xilinx devices, you have 32 ports into the two HBM stacks. There's some switching infrastructure that sits in between those ports and the actual memory controllers. And you can turn it on and off in the IP core configuration, but if it's on, then basically any of the ports can access any of the memory. Obviously, there are performance implications if you do that. And with the setup that I have, it's not cycle accurate. There's no contention or anything. Everything can access whatever it wants at the full bandwidth. But the point of these simulation models is just to support, you know, kind of functional verification that things are, you know, doing what they're supposed to do, and you can verify from the from the test bench side that the writes and whatnot are hitting the memories that they're supposed to hit, and so on and so forth. So it's good enough for, you know, integration testing and whatnot, but if you want, you know, accurate performance data, you know, you'll actually want to run that in the hardware, just to make sure that you're getting all of the nitty-gritty details. All right. So that brings me to updates on the Switch version of Corundum. So there hasn't been a whole lot of movement here. We had a meeting last week. Because, like I said, we're doing these. The plan is to do Switch development meetings that are alternating with the Corundum development meetings. So we had a meeting last week, and Carlos presented a few slides on, you know, what he's been working on, and we also got a new Ethernet switch repository set up for prototyping and development. So if you guys want to take a look at that, that would be cool. Carlos, I think, put that up just this morning or yesterday or something like that. I will go ahead and stick a link to that in the chat if people want to take a look. Let's see. Wait, where's the chat? There we go. Here's a link to that repository. It's just under the main Corundum GitHub organization. So right now, we're basically just doing kind of functional design exploration, where we're putting together some RTL it's only really intended for simulation. But the idea is we can get some of the, you know, basic switch architectures put together and tested, and we can use this to, you know, get our feet wet to make sure all of the simulation components are doing what they're supposed to do, and we can take a look at maybe some performance metrics of comparing some of the different switch designs, just to make sure everything makes sense. And so I think right now we have an input queued switch, very simple input queued switch, and then Carlos said he's going to put together a couple of other variants. And then I think the ultimate goal is to start chipping away at kind of the more final hierarchical crossbar design with the, you know, with the buffering in the sub switches, and, you know, we'll get all the kinks worked out of all of the arbitration logic and whatnot. So we decided to go ahead and put this up publicly, just in case anybody else wants to, you know, take a look at it and maybe have something to contribute, even if it's not code, you know, contributing some ideas or comments or whatever would be helpful. All right. And then also, just to mention, a switch design meeting, if the switch is interesting and you want to get some more information on that, join the switch channel on Zulip, and I'm going to be posting in there about the development meetings for the switch. And these are at the same time as the current Corundum developer meeting. So, but alternate weeks. So the next Switch development meeting would be next week, same time, and then the next Corundum developer meeting would be, in 2 weeks. And again, anyone's welcome to join. So if this sounds interesting, please join and contribute. All right. So that about rounds out the slides that I have here. Now I'll open it up for discussion. Does anyone have any questions or comments? Carlos, do you want to say anything about the repository that you put together?
Okay. Well, as Alex has said, anyone who wants to collaborate is more than welcome to do so. I just tried to organize some parts of the code. So because we are going to, at least it's my intention to keep record of any version that we are of the switch that we are doing. So for example, now that we have the input buffering switch, the idea is just to it is clear, obvious that this is not an optimal implementation. So in order just not to lose this code, we can do like separated files, indicating with a suffix at the end of the file, remarking which type of the switch this file corresponds to, and always keeping the last version or the most optimal one without this suffix. So for example, now that only the files named switch and switch crossbar are created. So for the input buffering switch, it would be like switch, the FIFO, no? And then added with IQ. Whenever another version, for example, the output Q switch comes in, we will name it like switch and then OQ. And for the other module called switch crossbar, the same. We will have switch crossbar OQ, switch crossbar IQ, and then switch crossbar with nothing else that will be representing the last version of the switch of this specific module. So yeah, anyone who wants to collaborate is more than welcome. Yeah.
Well, thanks for putting that together, Carlos.
Yeah, you're welcome. Thank to you all.
I guess we got our discussion out of the way before the status updates with all of the Zinc stuff.
Well, maybe I can throw a bit of spice in here. So unrelated to the switch, back to the SmartNIC. So one aspect, and I'm just looking to hear and hear what some of you guys who are playing with project and contributing to it know or can share. But one of the things that I've been kind of like struggling to understand is how is the Linux driver structured for scalability? And let me elaborate on this. So as far as I understand, SmartNICs can abstract away, of course, the data link layer, but they also typically include the transport layer and potentially much more stuff than that. So right now, as far as I understand the driver, it does offer an expose abstractions directly in the root file system of Linux, so that it can be understood as yet another networking interface. However, it does not change the primitives of a traditional Linux driver, so that it can be reused by higher level user space applications without any source code change. I was just wondering, are there any capabilities or any intention down the road to extend the current driver to support offloading the networking stack or not offloading it, meaning that maybe you can leverage parts of the SmartNIC, not necessarily the whole thing, UDP, IP, and then Ethernet. And have anyone thought even of pushing it the other way around, meaning that you can also offload maybe parts of the user space, for example, layers 5, 6, and 7 of whatever application that uses MQTT, for example. So has anyone done any work on that? And could you comment on how the current driver is structured for going in that direction?
Right, in terms of more offloading. Well, yeah, I mean, like you said, right now it's mainly in terms of just sending and receiving, packets without doing too much higher level stuff. So in order to do higher level stuff, you need the hardware to support that. So it's like, for example, if you wanted to do, UDP offloading, you would need to have, more of the UDP stack implemented in the hardware. So it doesn't really make much sense to add more to the driver if we don't have the, the hardware to interact with. I guess the other thing is I'm not sure exactly what some of this stuff would look like. So the driver right now is based on kind of existing Ethernet device drivers, and the kind of offloading that's supported on those. Although right now I haven't really done any kind of segmentation offloading. It's all been just scatter gather and checksum offloading and whatnot. So if you're talking about offloading, say TCP, I need to take another look at exactly what the kernel does for that, because I think there might even be a couple different possible implementations for that. But yeah, as of right now, that would require modifications to the driver. I guess I haven't had a compelling enough reason to sit down and implement that. Because like a lot of this stuff, it's all kind of need based. If I need that particular functionality, then I'll implement it and I'll make it work. So I haven't had an application for it. So I haven't, had the time to sit down and get all the kinks worked out to actually make it work. But in principle, it should be possible. I guess the other aspect as well is that right now the descriptor format in Corundum is pretty rudimentary. And that's one of the things that I'm starting to take a look at, is to implement kind of a more flexible setup for handling the descriptors. And with that, we'll have things like variable length descriptors where you can include a lot more information inside of the actual descriptors, which is going to be, I think, a requirement for a lot of these higher level offloads. But yeah, I mean, if there's a specific offload that would be interesting for whatever you're working on, that would certainly be something I think worth discussing to figure out, how that might fit into the rest of the design and, how that might work. Now, in terms of the application level offloading, we haven't done much more than just provide register access from user space. So, I mean, obviously you can do a lot with that, but it's a pretty generic capability. So, but flip side is applications can do all sorts of weird stuff. So if you try to get too specific, then that can, be pretty limiting. And also, for the most part, what I've been doing with Corundum has been more kind of on the packet processing side, where there isn't a whole lot of, application specific communication. It's kind of just configuration to set everything up and then it runs. So obviously, while it would be useful to, access the DMA subsystem and whatnot, I haven't had time to, implement that sort of thing in a nice way. Just because that hasn't been, something that I need. So if that's something that you guys need and you want to help, get that functionality fleshed out, we might be happy to discuss and figure out what that might look like.
Yeah, for now, as I said, so we have some ideas, but for now, understanding the building blocks and trying to get a grasp of the overall architecture and complexity of Corundum, now that we took that step back from Verilog Ethernet into Corundum. I guess one and this is maybe a lack of understanding from my perspective, but one pending item we had discussed internally was, so right now it appears that the Corundum implementation bypasses leveraging the LNS, Linux networking stack. It does use its own offloading, right? And so I was just wondering if mixing things together is something that would be of interest for the project, meaning that maybe you could expose, I don't know, in the sysfs or a flag. We've seen this in other smart NICs that would allow you to use the UDP IP implementation or not. And of course, that would require modifications in the PL design, but still, is that something of interest? And is my understanding correct right now, in the sense that you're not?
I'm not quite sure. I'm not entirely understanding what you're asking. So you're talking about exposing files in sysfs to do what?
So maybe let me break.
This is for configuration. You
Yeah,
can poke a
so
file
right
in
now,
sysfs.
our understanding is that right now the Linux networking stack is not being used when you use the Corundum smart NIC. So the interface exposed.
The Linux network stack is not being used.
That's our understanding. But again, we're taking small steps in here. When you are using the networking interface exposed by Corundum, the Linux networking stack is not being used. Is that assumption correct?
The Linux networking stack. So you're saying like ping itself doesn't work if you just run ping. It doesn't work because that goes to the Linux networking stack.
No, what I'm saying is that so ping will work because UDP IP is implemented in the PL, but you're not using the UDP and IP implementations that rely on the kernel drivers. And instead you're using the hardware implementation on the PL.
I mean, Corundum right now, it's designed specifically to use the Linux networking stack. And that's kind of the only way to use it. I mean, there's been some work to put together, a DPDK driver or potentially another user space driver that would, permit direct communication with the hardware. But this would also be, I think, mainly for exchanging packet data and not so much higher level stuff. Like if you wanted to implement UDP, you would use a software UDP stack, say in DPDK or something. So
okay.
Corundum doesn't know anything about UDP or TCP or any of these other protocols in hardware in its current incarnation.
Isn't it relying on Verilog Ethernet?
It uses the MAX and that's it.
Okay, so it's not using the UDP IP that's within. Okay. Okay, so that is the misunderstanding on my side. Okay, got it. Good. Okay, so we'll look back at it with that in mind. Again, just diving first steps into Corundum. So
yeah, sure.
Good.
Yeah, I guess it uses, what does it use from Verilog Ethernet? It uses mainly the MAX and then also some of the PTP components. So like the PTP clock and the PTP CDC logic and a couple of other things. But it doesn't use any of the Ethernet, ARP, IP, UDP stuff from the Verilog Ethernet stack.
Okay, so I guess I misunderstood that from the last discussion. I was under the impression that the recommendation of going from Verilog Ethernet to Corundum was because it was precisely packing it all together plus exposing through a Linux driver, all of it from the Linux perspective, and that was the reason why it was easier to leverage it. But I guess I just misunderstood that completely, and I need to get back to it. Okay.
That's all right. All right, so do we have any other questions or comments? If not, then I guess we can adjourn for today, and we'll see you guys in 2 weeks or maybe 1 week if you're gonna get involved in the switch design. So let's see, I guess the switch dev meeting, the next one will be on April 3rd, and then the next Corundum developer meeting will be on April 10th. So all right, I will see you guys later. Thanks for tuning in.
Thank you, everyone.
Thank you, everyone.
Okay, thank you. Bye.
All right, talk to you.